Hello, today we're going to talk about profiling application I/O with Altair Breeze. Breeze is a unique profiling tool that collects detailed information about the way applications access their data. One of the views we're going to be looking at today is this one here, which is the I/O summary, breaking down I/O into good and bad, so that you can easily identify whether the application has bottlenecks and assess the impact it has on any shared file system in your environment. There are many reasons why you might want to profile I/O. You might be looking to accelerate the performance of an application that's going to be running at scale. You might have moved the application into a new environment or upgraded to a new version and seen a downgrade in performance. It's not uncommon, for example, to migrate an application to the cloud and then not necessarily see the performance you're expecting, and Breeze can help you troubleshoot that. You might also be looking at why an application works for one user and not for another, and you may well be tuning third-party applications. It's pretty common for HPC systems to run lots of third-party tools. You can't necessarily change the way they access data, but you can look at deploying them in the right way to mitigate any I/O issues. The Sanger Institute is one of our customers who do all of those things with Breeze. In particular, they have used Breeze in their cancer team to find out why they had low CPU utilization when it should have been high. Breeze was able to find some I/O bottlenecks so that they could see significant gains in performance. So the first thing you need to do is to trace your application. Breeze comes with a wrapper script for doing that. So you just run trace program followed by your application and any arguments. If you want to submit that to a batch scheduling system, then you would send all of that to the scheduler. In this case, I've already traced the application and loaded it into Breeze. This is an HPC application used in the semiconductor industry. And the first thing we see is the I/O summary. So this is telling me the program ran for 52 seconds, so just under a minute. And it did 4 seconds of bad I/O, 1 second of medium I/O, and 1 second of good I/O. Now, bad I/O is things that we categorize as I/O patterns that could harm shared file systems. So in particular, small reads and writes. We're spending quite a bit of time there. Obviously, it's only 3 seconds, a little under 4 seconds. So if we removed the small reads and writes, this application would run a little faster. But you may well notice that the performance of the file system increases or improves. So it can be worth doing that for the overall performance of the system, even if an individual application doesn't improve. We then have various metadata operations. Opens and closes can be very expensive, and often applications open a file every time they read or write to it. That's fine if it's separate files and that's needed by the application, but it can cause performance issues when you're hitting a metadata server. If I expand the number of small reads and writes, you can see it's mostly small reads. And you can see that actually for nearly every small read this application performs, there is an open or a close on an unused file and an open or closed on a seldom used file. So it looks like every time the application reads from a file, it opens a file which fails, and then it opens the file it wants to read from and then closes it. So this here implies that we have some bad I/O patterns. Certainly looking at the small reads and writes and the patterns of opens is a good start when looking to understand application I/O. At the bottom here, you can see a list of processes, and it's telling me the contribution. Most of the I/O comes from this single binary Vivado, which is the main application. If you have a more complex workflow, this can be really helpful for zooming in on the process that's of interest. The next place to look is at the I/O by mount point. You can find that in the Files view by selecting Mount Point. Here you can see a list of all the I/O operations listed by mount point. This application ran on the cloud against local storage. If you had shared file systems or remote file systems, those would appear here as well. By default, you see the number of calls, but I like to look at the total latency. You can see most of the bad I/O in the form of small reads that we saw on the I/O summary was actually to /proc, so just the application reading information about itself. We also have 11 seconds of I/O going to /dev. That's not shown in the previous view because normally that is a blocking read on a pseudo terminal, so something like standard in. If we expand that, you can see 9 seconds for a single read operation. So the real I/O, as it were, just took 152 milliseconds. I can also look at the duration view to find out where the application's spending its time. So I can find the application that started first, ended first, ran for the longest, as well as sorting by the amount of I/O. Again, not surprisingly, it's this Vivado process that does most of the I/O in this case. And if I look over on the right, I can see more detailed information about the I/O patterns. So I can see the data throughput for the reads and write bandwidth. I can see the operation count. And again, here it's very clear to see that for every read, we have a metadata operation. You can also see the CPU load for that process and also the memory consumption. You can also look at the profiling data views for getting an idea for how your application is accessing data over time. So here we've got file system I/O counts. I can switch through different operations. I can look at reads, writes. Let's look at open calls. Again, you can see very heavily loaded at the beginning and matches the patterns that we saw for an individual process. This is aggregated for all mount points, but I can also see the data broken down for specific mount points. So if you're looking at the impact on a shared file system, you can see that here. If you're looking to understand the performance of a file system, you can look at file system I/O latency. So here we've got the minimum, maximum, and total amount of time spent doing a particular operation, in this case still open calls. And here we have the number of calls that fell within particular buckets. So I/O calls that complete very quickly are likely to be cached or on solid state storage, whereas operations that take longer are cache misses and potentially network storage or spinning disk. This was all on solid state, so the I/O operations completed very quickly, but in an application running on shared file systems, you would see a much greater variation. As you can see, Breeze lets you explore the I/O patterns of your application in a number of different ways. We also looked in an earlier demo at application dependencies, and this can be a great way to understand where you're spending your time as well. Looking at which file has the most I/O calls is a really interesting way to understand your application. If I sort by the number of open calls, immediately we learn something. You can see that most of those open calls were actually to proc self status, to check the status of a particular PID. And the real opens, if you look here, are actually, and then there are hardly any real opens here to speak of. And so that's why it's really important to dig into the information, look at the summaries to see if it's worth spending your time on the application. And then that's why it's important to dig into these views to really understand how the application is spending its time. If you want to share some of this information and you don't want to have to ask your colleagues to fire up the data in the GUI like I have done here, you could also generate a health check report. I've generated one earlier. So in the health check report, again, we've got some program information, dependencies, and network I/O, but we also have the summary of time spent in I/O. We have the time spent in good, medium and bad I/O, as well as many other metrics that let you explore the application and how it's spending its time.